Permanent magnets made of neodymium, iron, boron, and cobalt were sintered as well. The alloy resulted quite fragile and therefore rings were not sintered without being broken. This happens because the more dramatic thermal gradients between sample and tools did not make possible to have a good densification and therefore high mechanical strength. Process parameter ranges were similar to the titanium case. Due to the high brittleness, the original powder was pre-treated to be refined and therefore increased the mechanical strength. To do this, high-energy ball milling was applied. A ceramic bowl filled with 100 spheres was rotated at high rotational speed. The impact of the spheres with the powders provoked the refining of the particle size. Here is shown the ball milling process. Two main directions of rotation are defined, one for the rotary base and one for the ball. Both rotate with the same RPM but in opposite direction. This made possible the impacts between powder and spheres. And here the results from ball milling are shown. The powder, as is it possible to see, is clearly refined. Different structures are achieved, as pictures are showing, which are shown to be more complicated than titanium 1. After sintering, samples made of neodymium, iron, boron, and cobalt were magnetized and analyzed in terms of magnetic properties. Magnets proved to be stronger when the dendritic structure did not appear, as post-processing magnets were electroplated with nickel, copper, and nickel in order to be preserved from corrosion. So, resistance sintering proved to be a successful sintering approach, enabling the production of high density and quality components in few hundreds of milliseconds. High quality is obtained with a fine optimization of the main process parameters, which were identified as the electrical current, the sintering time, and compaction pressure. Titanium was tested and properties were compatible with the bulk ones. Permanent magnets were sintered and the magnetic strength was comparable with commercial magnets. The maximum density achieved was 96% relative for both the materials. As the future works, the resistance sintering approach has yet a wide field of application which is still unexplored. Optimize the homogeneity of the density inside the sample, testing new shapes, for example microgears, to be functional employed in electronic and mechanical appliances, functional tests on magnets and durability tests, direct temperature measurements. The industrial application of this approach will be beneficial to increase the productivity and reduce the production costs.